Yeah, gateway on Friday. Today is Wednesday the 21st, September 2016. Friday the 23rd is going to be the gateway. Let me remind you about things about it. First of all, we will take it the second half of class. We'll only have a first half for lecture, and then we'll take the gateway, and you can leave after the gateway is done. Gateway is 6 questions. You've got to get 5 out of 6 exactly right with no partial credit. And that does include making sure you add plus C at the end. And they're all indefinite intervals, so they all need plus C's at the end. I have to count wrong. It's a department policy. Okay, you have to strive for 5 out of 6 exactly right. Plus C needs to be there. You know, what should you practice? You should practice memorized integrals, including the integral of secant squared, is tangent of x plus c, the integral of, what else to know? Integral of 1 over 1 plus x squared is arctangent of x plus c, or inverse tangent of x plus c if you prefer, both right. Integral of 1 over square root, we don't really emphasize this one as much, of 1 minus x squared is arcsine of x plus c, or inverse sine of x plus c. Those are all memorized things. Integral of 1 over x is natural log of the absolute value of x plus c. Do put the absolute values in there for full credit when you integrate 1 over x. When you integrate, by the way, natural log of x, for example, you use integration by parts. You don't need the absolute value signs when you integrate that because the domain is already assumed to be only positive numbers when you integrate natural log of x. But when you integrate with 1 over x, the domain is everything except 0. Positives and negatives, we want to have the absolute value signs in there when you integrate 1 over x. That also comes into play with integrating by partial fractions. It is, you know, the book has some harder examples of partial fractions. We are skipping those at least for the moment. We might come back to them later. Harder examples of partial fractions. On the gateway, it's easier, except there is the tricky thing where if you, for example, have one factor that's something over, say, 5 minus x, with a minus sign there, 5 minus x, you got to deal with a minus sign when you integrate too, because in your mind you can imagine doing a substitution, w equals 5 minus x, then dw would be negative ds. So that came up in class last time, could come up on today's quiz, so practice that. Integration by parts, substitution. And another substitution kind of problem that's a little bit more irregular is with powers of cosines and sines, where at least one of the powers is odd. Those are the kinds of things that come up.
Will we need to memorize any of the tables in the back of the book?
I said just through the first 7 of them.
So just memorize them?
It's the ones I already said to memorize, not the other ones. So it's the first 7 back there. You actually have to memorize more than that, though. I mean, you got to memorize what the integral of secant squared is. That's not back there. Memorize what the integral of 1 over 1 plus x squared is. But the other equations you see in the table don't have to be memorized. I guess 24, you're almost memorizing that one. And 28, you're almost memorizing that one with arctangent and arcsine. We can't do derivatives. So, but the rest don't have to be. I will grade them as soon as possible and give you your feedback about whether you passed or not. If you do not pass, then you've got to retake it, a different version, different questions that was similar, outside of class. Is that your question? Okay. So you have to schedule it with me. All right, first half of class today, we are going to do vectors. I'm going to make sure we get vectors in, including velocity vectors, though if you're up to date on the extra videos to watch, you should have learned about velocity vectors already. Position vectors and velocity vectors. We are just, for the moment, approaching it geometrically. Maybe later on we'll be a bit more algebraic in how we approach them. I'll bring in a little bit of algebra here today, but not much. Mostly so we can focus on good examples for discussing numerical integration. Okay, that's besides the usefulness of parametric equations and curves. It's also context for doing numerical integration because the integrals are typically pretty hard to do, even for simple examples. Then in lecture B, we get into improper integrals and probability. We're going to go back to probability and think about that application in the context of what are called improper integrals. All right. I typed in the Mathematica code ahead of time, so you don't have to spend so much time on that. So this is the same example as we saw on Monday. X was cosine of 3t. Y equal g of t was sine of 5t, two trig functions with different frequencies. C of t is the parametric curve that in Mathematica you have to put inside curly braces as a list. When you write it by hand, C of t, there's two ways you could do it. You could either write it as a point, f of t comma g of t, and think of it as a moving point. And that's what we've done so far. But actually, you can use vector notation. If you read Appendix D, I think it was, you can actually represent this as something called a vector, f of t times I plus g of t times j. What in the world are I and j? Well, actually, the book puts little vector symbols above them, like little arrows like that. I like doing what the physics professors do and put a little hat above I and j. They call them I hat and j hat. Okay, if you've never had physics, just accept that. What those are is they're called the standard unit vectors. Okay? Hats on variables are actually kind of cute, don't you think? I hat and j hat, they're kind of cute that way. Well, they're called the standard unit vectors. And in an xy plane, I hat is an arrow that points directly to the right and has a length of 1. One right there. It points directly to the right and has a length of 1. And j hat is a vector that points directly upward and has a length of 1. So these marks are at 1 on the x and y axes. This vector is I hat, and this vector is j hat. When you put the hat, you don't bother having to put a dot, by the way, either. Okay? And effectively, by writing the point in this way, you're saying, well, if f of t and g of t are positive, I have to take f of t times I hat, essentially scale I hat up by the factor of f of t, if f of t is bigger than 1, to get a vector that's f of t units long, if f of t is positive. So this vector is f of t times I hat. And if g of t is positive and in fact bigger than 1, it gets multiplied by j hat. You're scaling j hat up by a factor of g of t. The length there is g of t, but the vector itself is called g of t times j hat. And by adding them, essentially you are creating a rectangle that looks like this. And this c of t as a vector, as an arrow, starts at the origin and points to that other side of the rectangle. That point right there would be the point f of t comma g of t. The arrow that I drew from the origin to that point would represent the vector. So we actually have flexibility. We can sometimes think of c of t as a point and sometimes think of it as a vector. It really doesn't matter sometimes. You can think of it either way. Okay? It's probably more useful to think of it as a point when you're thinking about the motion. But when you're thinking about the position vector and its derivative, which is called the velocity vector, it's better to think of it this way. This way algebraically, this way as a picture. So again, this picture applies when f of t and g of t both have value bigger than 1. Okay, so that I hat and j hat get scaled up by those factors. Anyway, as far as Mathematica is concerned, it's just a list. We use parametric plot to plot the curve. We use list plot to plot the dot. I'm going to use graphics and arrow to plot the vector. I did show you how to type that out once, although I didn't use the thick and blue inside there. So here we have the motion. This is the Lissajous curve here. We see the curve itself. More importantly, we see the black dot that is moving. You could pretend it's a car moving around in a parking lot with this kind of motion. And we see the blue arrow pointing from the origin to the car as it moves. That's called the position vector of the car. Thinking about the car. Okay, I guess I could have, like with the balloon, I suppose I could have gotten a little car actually in there. I tried to make that go, but that would have been a fair amount of work and I was busy. Okay? The velocity vector v of t is going to be the derivative of the position vector. Again, here I'm thinking of c of t as a point, but I can think of it as a vector. When you think of it as a vector, not only do you do this, but it's common in books at least to boldface it, or to put little arrows on top of it. You might think we should put full arrows, and you certainly can, but we get a little lazy, and we put half arrows. It's a little less work to make a half arrow than to make a full arrow, right? Save a little writing, make a half arrow. I'm being only somewhat joking, okay? If you have lots of vectors, it is actually quicker in the long run to only make half arrows. You can find the velocity vector by differentiating the position vector, which is exactly what you would think it would be. Just differentiate f and g. Make a new vector where f prime is in front of the I hat and g prime is in front of the j hat. And if you're thinking of it as a point, which you can, you could write it using point notation. However, it's a good idea with velocity vectors to not base them at the origin, but instead base them at the location of the object as it moves. So it's a moving vector that's always starting at the location of the object as it moves. I'll make my velocity vector red here. So I'm going to add in a red. Add in another arrow command. This is a bit tricky here. Since I want my velocity vector to start at the location of the object as it moves, I'm going to put a c of b in here right away instead of a 0, 0 like I did with the position vector. So that's going to be the starting point of the arrow for the velocity vector. And the ending point can be found by doing c of b plus the velocity vector, which can be calculated as c prime of b. And Mathematica, if I put c prime of b in there like that, does know calculate the derivative of c. Where does the plus come from, you might wonder? Let me not bother explaining that today. But just observe what happens with the velocity vector. You might need to increase the plot range, it looks like. It's pretty long sometimes. It's pretty long when the object's moving fast. It's shorter in the curves where it's moving slowly. You can actually see the full vector, like right now, and right now. And it's always tangent to the direction of motion. In fact, its length changes. Its length is the speed. The speed is the length of the velocity vector, it turns out. And again, it points in the direction of motion at any instant in time. It is the instantaneous rate of change, so to speak, of the position vector. And the extra videos get into that a little bit, about why that makes some sense. If we go on a wider window here, change my plot range to maybe -4 to 4 here. Well, it's still too long there initially to see the whole thing, but we'll see it better overall. It changes not only direction, but changes length. It's short when it's slow motion, it's long when it's fast motion. In fact, again, the length is the speed. So at the moment, I'm just wanting you to understand that basic intuitive idea. What we want to do here now, though, today, in Lecture A, we want to focus on integration, numerical integration. I want to find the distance traveled. I showed you last time that NIntegrate is Mathematica's way of doing numerical integration very quickly. And in fact, I'm doing numerical integration of the speed function for any upper limit of integration, little t, to give me my distance function. distance traveled from time 0 to time t. This was entered, and we can plot it. And over the interval from 0 to 2 pi, here's what the graphs look like. It takes a little while to compute it because it's doing so many integrations. To create this blue curve, it's doing lots and lots of intervals before it produces the output. That's why it's a little slower there. It's integrating the red curve to get the blue curve. The red curve is the speed, goes up and down, but it's always positive. The blue curve is the distance traveled. It's always increasing because the speed is always positive. But its slope changes, gets higher and lower. It's a high slope when the value of the red is high, like right there. It's a low slope when the value of the red is low, like right there. You want to know the distance traveled up to any moment in time, like time 2 we saw last time? It's about 8.06982. That's the value of the blue graph at t equals 2, right there. It's integrating the red graph to get the blue graph. This is, if you watch the videos, this is the main thing I emphasize in all those videos. In the rest of lecture A today, I'd like to focus on smaller intervals here. First, I'd like to focus on an interval where the speed function is monotone and decreasing. From 0 to that minimum value, that local min for the speed graph, the red graph. If I set the derivative of the speed equal to 0 and solve for t and use something called find root to estimate that value of t, it is close to 0.3, that was my guess. 0.29268 is the approximate t value where you have that local minimum. So over that interval, the speed function is monotone decreasing. It doesn't go up or down, it just goes down. And if you've done your reading about numerical integration, you should know something about that. Let's zoom in on it. Focus mostly on the red graph here. It's a decreasing function. When you do a left-hand sum for a decreasing function to approximate the area under it, do you get an overestimate or an underestimate? Yeah, overestimate. Why? Draw the picture. For each subinterval, I'm just drawing sort of random points here. Take this subinterval here. You use the left endpoint to determine the height of the rectangle. I'm not drawing this perfectly, but that's the idea. And you use left endpoints for all the intervals for left-hand sums, and when your function is decreasing, you're going to get areas that are too big for all those rectangles when you add them up. Whereas a right-hand sum uses the right endpoint of each interval, and you get rectangles that look like this. So the right-hand sum would be an underestimate in that case. Left-hand sum would be overestimate, right-hand sum would be underestimate. There's the geometric reason why. You should know these facts. Let's confirm it by getting Mathematica to do the summations for us. You did a little bit of this kind of thing by hand. You got this interval from A to B. You're breaking it up into n subintervals, each of length delta t, which is b minus a over n, the length of the entire interval divided by the number of subintervals. For the general interval from ti to ti plus 1, your left-hand sum is found by adding. I goes from 0 to n minus 1 f of ti times delta t. I guess I'm not really thinking about an arbitrary subinterval here, but actually it's probably better to label it in the picture on the board is slightly different. Call this t sub I minus 1 and this t sub I. That is the ith subinterval, so to speak. Ith could, I could be 5 and then it would be the 5th subinterval. I could be 6 and it would be the 6th subinterval. For the first subinterval, you use t sub 0 to plug into the function. That's the first term in the sum. That's the height of the first rectangle. the left endpoint of the first subinterval, times the width of that interval, etc. There's the left endpoint of the second subinterval, t sub 1, etc. The left endpoint of the last subinterval, b is t sub n, so the left endpoint of that last subinterval is t sub n minus 1. And that is the last term in the left-hand sum. I starts at 0, that's the left endpoint of the first subinterval. Ends at n minus 1, that's the left endpoint of the last subinterval. The right-hand sums take the right endpoint. Now you let I go from 1 to n instead of 0 to n minus 1. And you start with f of t sub 1. T sub 1 is the right endpoint of the first subinterval, etc. You end at f of t sub n. Okay, this should be all reviewed. You should feel like this is very familiar. Let's get Mathematica to do this. I need to specify a and b. A is going to be the starting time, which is often 0. B is going to be the ending time. I'm going to take that to be, in this case, 0.292768. Where this function, the interval where this function is decreasing. 0.292768. I'll type that in for b. Delta t is b minus a over n. Notice that I'm emphasizing that's a function of n, the number of subintervals. Doing that on Mathematica, I don't have to write that when I write it by hand. But I'm ultimately going to think of n as my variable. I want to increase the number of subintervals and the number of rectangles to approximate the area. This thing has got to depend on n. The t sub I depends on I and n. And the general formula for it, when you write it by hand, is t sub I equals a plus I times delta t. I'll go ahead and type it in like that. A plus I times delta t. But delta t depends on n, so I need an n there like that. I'm going to program Mathematica to do these sums in the general case. Now we're set up to do the sum. Let me just continue in the same cell. I'll separate my code by semicolons. Like last time, I'll call it LHS of n. That'll be a left-hand sum. Click on the basic math assistant over here where the summation is, right down there. I goes from 0 to n minus 1. I'm plugging these things into the speed function, so I need the speed function here. T sub I is t of I comma n. Delta t is delta t of n. Okay, the speed is like my f. Compare this with this. The speed is my f. The t of I comma n is the t sub I here. The delta t is the delta t of n there. Those both depend on n, so Mathematica needs to know that I need to put that in there explicitly. I is going from 0 to n minus 1. Right-hand sum is going to be practically the same thing, except I got to just change I to go from 1 to n instead. So copy and paste that. Change the L here to an R. Change the 0 to a 1. Change the n minus 1 to an n. And then this other method, the trapezoid method, is, in our book's approach, just the average of the left and right-hand sums. There are other textbooks that treat it differently, that treat it as a summation. Okay? But our textbook takes the approach of saying the trapezoid method is the average of the left and right-hand sums. And so now we can approximate it, and because the function is decreasing over this interval, remember the left-hand sum is going to be too big, the right-hand sum is going to be too small. What is a more precise answer? That would be dist of 0.292768. What does the left-hand sum give us? When, say, n is 10, And what does the right-hand sum give us when n is 10? This is going to be the most precise answer, the first output. This is going to be too big, this is going to be too small. There's the most precise answer. That's too big, that's too small. How about the trapezoid rule? What's going to go on with that here? Going back to the picture, it turns out that the trapezoid rule really is giving you areas of trapezoids. For your different subintervals, you end up calculating really the area of that trapezoid there as your approximating area for that subinterval. It really is doing that even though we're not explaining why. That happens for each subinterval. And the fact that the graph is concave down, not over this entire interval, but at least up to there or so, would mean when your graph is concave down, it seems like the trapezoid rule is going to be too small. The area is underneath the entire area under the graph. Now this graph does go concave up over here, for which the trapezoid rule gives you an answer too big. The approximating trapezoid looks more like this, in that case. But this graph does seem to be sort of more concave down than concave up. I'm going to guess the trapezoid rule is going to be too small, though I suppose this guess could be wrong. Oh wow, it's real close, look at that. To 5 decimal places, it's the same. Really, really close. That doesn't typically happen. Let's try a smaller value of n with each of these. Let's try n equals just say 5. Wow, it's still giving one exact answer, even though the speed function is complicated. That surprises me. It is a bit too small when n is down to 2. Let's try 3s. Okay, again, a bit too small. There's the most precise answer. This is too big, this is too small, this is a bit too small. Trapezoid is better than both the left and right hand sums. Can that error be quantified? Yes, it can. You can quantify this error in each case by taking the most precise answer minus the approximation. The left-hand sum was too big, so this difference is going to be negative. The right-hand sum was too small, so this difference is going to be positive. Notice that those errors, one is negative, one is positive, are approximately the same in absolute value. And that's pretty typical for monotone decreasing or monotone increasing functions, that your left and right hand sums have opposite signs and are approximately the same in absolute value. What about the error in using the trapezoid rule? In this case, it's positive because the trapezoid rule was too small. If that number is smaller than that number, the whole thing here, the difference is going to be positive. It's smaller. It's positive, and it is closer to 0. It is smaller than these. The trapezoid rule indeed is doing better. I want to take a few minutes just to introduce you to the midpoint rule, then we're going to have to continue with numerical integration in lecture B. The midpoint rule takes, instead of the left and right hand endpoint of each subinterval to create the rectangle, it takes the midpoint of each subinterval. Mid of n can be done as a summation. What happens with I? Well, you could do it from 0 to n minus 1 or 1 to n. It actually doesn't matter. Though, depending on which one you pick, the expression that goes next could be different. Delta t is still the same. The only difference is what goes inside of f. That's the only difference. In your generic ith interval, where this is t sub I minus 1 and this is t sub I, the midpoint is their average. T sub I minus 1 plus t sub I over 2. That's what's got to get plugged into f. That determines the height of the rectangle for the midpoint rule. In Mathematica, if I'm doing it with the notation I've had here so far, I'd have to do the same thing. I've got to take those two numbers and add them. Notice I've got something divided by 2 going into the function f. It's t sub I minus 1, which would look like this, plus t sub I, which in Mathematica, based on how I've done it, would look like that. With I starting at 1, this is doing the right thing. That's the midpoint of the first subinterval. If I started I at 0 instead, then I'd want an I there and an I plus 1 there. But since I'm starting at 1, I can have an I minus 1 t sub 0 for the first term, and an I there t sub 1 for the first one, the first subinterval. This is going to calculate the midpoint approximation, and when n is 3, we are way off here. I must be doing something wrong. Oh, f. That's why. I want speed. Evidently, f is defined to be something else. It was cosine of 3t. Okay, there's the midpoint approximation when n is 3. Pretty close to the most precise answer here. A little off. A little too big, it looks like. So this difference, again, the 2.292768 is just the right end point of the interval on which the graph was decreasing. It's a little too big. This difference should be negative. And it is. A little surprised by this. Typically, the midpoint rule does about twice as well as the trapezoid rule, but in absolute value, these numbers are not too far apart. I think if n were bigger, maybe I'll go back to 10, we'd see a bigger difference. Let's let n go back to 10. And see if the error for the midpoint rule, the second one here, is about twice as close to 0. Evidently it's not. Am I doing something wrong still? Got the same thing as that. Oh, it's because I used the 3. Sorry. It's not a ton closer to 0. It is a little closer to 0. I'm thinking it's because the graph is, it's mostly concave down, though a little bit concave up, and so maybe because that mixture of concave down and concave up, and that midpoint's not doing twice as well as the graph. Quick question?
Could you show what the mid is doing with that graph, like you did with
okay, let's do it after the quiz. Okay, we're already late for the quiz. Let's take the quiz.